Now let's examine the relationship between the input impedance Zin of D and the characteristic impedance Z0 and the load impedance ZL of a terminating line. We previously established the relationship between Zin of D and the gamma 0. We also found the relationship between gamma 0, Z0, and ZL. Our objective now is to describe Zin of D in terms of circuit parameters without having to refer to gamma 0. By replacing gamma 0 with Z0 and ZL, we can now express Zin of D directly in terms of Z0 and ZL and the position D. When we examine the line from position L to the right, the impedance we observe now may not be exactly equal to ZL. This is because reflections can cause the line to alter the load impedance. This phenomenon is known as the transmission line effect, and it is an important discovery. We now understand that when we use a line with a different length, the load impedance at a certain operating frequency is converted to a new impedance. Alternatively, if we use a line of a fixed length, the input impedance experienced by the signal will vary depending on its frequency. The line length is a relative value in relation to frequency, and we use electrical length to describe it. When discussing this, engineers can ignore the actual frequency and instead use something like 1/8 wavelength to describe the line's length. Besides the wavelength, the electrical length can also be expressed in terms of angles. For instance, we can use the phrase a half pi line to refer to a quarter wavelength line.